on. So first of all, we got the result. It was called quadratic reciprocity, and the result is definitely something you should know, and you should know how to apply it, how to solve problems using this result. The proof of this result is in the pictures. Well, it's okay if you don't understand all the details. For the sake of just passing the course, it's even okay if you don't understand it in the proof at all. It will not be I will not test you on this proof in any way. I also made two mistakes which cancel each other while proving it. So somehow at one spot I counted some extra points. We had some picture like this triangle, and somehow I counted the points on the x-axis as well, which I shouldn't have done. And another time once again I had to do with x-axis. I did the same computation with 2, and then I counted the x-axis, and I counted the number of points here, one more, and together this mistake somehow cancelled out each other. So let's start with just formulating once again what is quadratic reciprocity. And today I just want to solve a couple of exercises about it. So quadratic reciprocity looks like this. If n, q are all primes, then q over p, q is a quadratic residue modulo p. If you want to understand whether it's a quadratic residue, you can do it as follows. You compute -1 over 2 minus 1 over 2 times is under symbol of p over q. So this thing tells you whether p is a quadratic residue modulo q. This is good if you want to understand whether something is a quadratic residue modulo prime p, you factor it to product of primes. But there is, not every prime is odd, so there is a supplement to this law. Whether 2 is a quadratic residue, and we decided as follows, and I made some mistake here. It should be like this. It's -1 to the power equals 1 over 4, integer part, and it's still 1 plus -1 modulo 4 modulo 8, and it's -1 is plus -3 modulo 8. So there is no mistake here. Last time I did make a mistake here. Well, the formula that I wrote turns out it still works, but I didn't derive it correctly. So this formula is what we should have derived last time. And finally, there could be a minus sign in front of the number, so we want to understand that the -1 is a residue, and for this we have the following. -1 is a residue modulo p, if and only if p is 1 modulo 4. So that's quadratic reciprocity, and what it allows you to do is understand when a quadratic equation is solvable modulo p, modulo a prime number. So for example, let's see, is x squared is equivalent to 15 modulo 59 times 73. So, which means either this one solution. Times 73. So this is a pretty large number, something like 3,000 maybe. I thought, yes. So first of all, this number is not a prime number. It's given as a product of two prime numbers, but it itself is not a prime number. So we won't be able to use quadratic reciprocity directly for this number. But we can apply Chinese remainder theory. This equation is solvable if and only if it is solvable modulo 59 modulo 73. If you have a solution modulo each one of the primes, using Chinese remainder theorem, we can combine them and get the solution modulo 15. So, duality x squared is equal to 15 modulo 59 times 73 is a solution. If and only if both x squared is equal to 15 modulo 59 and x squared is equal to 15 modulo 73 have solutions. And that's Chinese remainder theory. Yes.
I thought Chinese remainder theorem only worked on linear congruences.
The Chinese remainder theorem, well, here you, in a sense, you look at linear congruences in the following sense. You want x squared, this number, to be 15 modulo one number, and you want this number to be 15 modulo another number. It doesn't matter whether it's...
We remove the square, so k could be not squared. So if you replace x squared with y, then and then you split it up using CRT, the y that it implies exists might not be a square.
No, it will be a square, because if y is congruent to x squared, if you find some number x such that y is congruent to x squared modulo p and y is congruent to x squared modulo q, then this number is still congruent to x squared modulo pq.
Is the converse true?
The converse is also true, yes. So this is just, well, it's about, basically even here you can say something like this. I don't even need the full power of Chinese remainder theorem. I'm only saying that x squared minus 15 is divisible by 59, and x squared minus 15 is divisible by 73. And the same is saying that x squared minus 15 is divisible by the product, because these are relatively prime. So, to be honest, I'm not even using Chinese remainder theorem to the full power of it. But I don't see that there is any problem with using it. Okay, I mean, you're right that if something is some square modulo p, it is the same number is a square modulo q, it doesn't, well, some square, it doesn't imply directly that it is a square modulo pq, but here we have, it's not just s square, it's the same square. Okay, anyway, this here is, this is a case that this thing is equivalent to saying that 59 times 73 divides x squared minus 15. If you want to leave, 59 divides x squared minus 15, and 73 divides x squared minus 15. Oh, wait, I see what you mean.
Well, when you're asking, for the question you're asking, is x squared equal to 15 mod 9 by 70 solvable? You don't need the two-way implication in this case, do you? All you need is that if the two are solvable, then the full one is solvable.
Yes. So definitely, if this is solvable, each one of those is solvable. But what he's saying is, suppose that I have that 15 is the square of something, and modulo 59 is the square of something else, modulo 73. Will I be able to find some actual number whose square is equal to 15 modulo times cube?
Yeah.
And
Because then
I'm not sure.
no, because when you solve each of those, won't you just get a linear like y congruent to one
Yes.
thing 59 and y
Yes.
congruent to another thing 73, and then you can apply CRT.
Yes, exactly. So, but then why this will be square modulo this thing? Okay, definitely, oh, this implication is absolutely obvious. The other one, I'm not sure. Sorry?
I mean, the transfer theory can let us know that in this way, we can get the answer correct. Not really sure the universe case.
I mean, it's definitely true that, sorry, so this step is definitely true that, no, if and only if the system is solved. So definitely, this equation is equivalent to the system of these two equations. Well, so here we have both implications. And the next thing I want to say, well, it seems not actually not to work both ways, but at least in one way it does work. In particular, 15 is a square modulo 59, and 15 is a square modulo 73. So in the opposite direction, I'm not sure that this works, because it could be a square of something, of one thing modulo 59 and of another thing modulo 73, and then we find something. Oh no, of course, yes, of course it works also. Sorry. I was confused for a second. So, if it is a square of something modulo 59 and is a square of let's say I'm definitely sure about this implication. The other way I would have to think a little bit more carefully. I think that the other implication also works, but no, I'm not sure. Sorry. Maybe let's let's maybe try to figure out whether now the implication also works. Yes.
Well, if you replace x squared with y, then it's obvious that if you have y congruent to 15 mod 59 and y congruent to 15 mod 73, the only solution is y
Yes.
congruent to 15 mod
Yes.
that, right? So let's say you have two solutions, x1 and x2, for 15 mods for x1 squared.
If x1 squared is congruent to 15 modulo 53, and x2 squared is congruent to 15 modulo 79 and 3.
Then CRT.
By Chinese remainder theorem, find x, which is congruent to x1 modulo 53, and x, which is congruent to x2 modulo 79. Then x squared is congruent to 15 modulo 59 and 73. Right? Yes. And then x is congruent to 15, x squared is congruent to 15 modulo 53 by 79. Yes, it does work both ways. I mean, you're right, it's kind of, I mean, there is something to prove in the opposite direction. So it could, if 15 is the square of something, modulo 59, and is the square of something, even if something else, modulo 73, there is still one number which is equal to x1 modulo this and x2 equal to modulo 73 by Chinese remainder theorem. You can find one number, replace this x1 and x2 by one number modulo 53 times 79. Okay, so this equation is solvable if and only if 15 is a square modulo this number and 15 is a square modulo that number. But this thing we can actually check. We have quadratic reciprocity for this. How do we compute 15? Another symbol, 15 over 59. Okay, yes. The first step, write 15 as 3 times 5. Because otherwise, quadratic reciprocity just doesn't work. Now, Legendre symbol is multiplicative. So it's 3 over 59 times 5 over 59. Now we can use quadratic reciprocity. We support primes. 3 is minus 1 modulo 4, and 59 is also minus 1 modulo 4. So this is minus 59 times 3 times 5 is 1 modulo 4. So here I don't need a minus sign, just 59 over 5. Also in brackets. Next step I just, so here I applied quadratic reciprocity. Next step is kind of obvious one. Whether 59 is the quadratic residue is the same as, well, I can change 59 by any other number which is equivalent to it modulo 3. So it's the same as minus. 59 is minus 1 modulo 3. And this one is, oh, minus, you can say minus 1. Let me, for the sake of argument, say that it's 4. And now, once again, we have minus 1 modulo 3. Well, we can either see directly that it's not a quadratic residue, or if you can say that it's minus 1 to the power of 3 minus 1 divided by 2. And 4 is definitely a quadratic residue, it's 2 squared. So it's times 1. It's minus 1. So this equation is solvable. 15 is equal to x squared modulo 59 is solvable. But that's not the end of it. We also want to compute what is 15 over 73. Well, we know what to do. Factor 15 is sequence 5. Use quadratic reciprocity. 73 is now 1 modulo 4, so in both things there will be no sign. Replace it by the residues modulo 3 and modulo 5. 1 and 5. Oh, wait, sorry, 2. 1 is a square because it's 1 squared. 2 is, well, let's compute by our formula, minus 1 to the power integer part of 5 plus 1 will be. Negative 2 by, oh, it's 3, yes, or negative 2. Well, maybe let's use the formula for 2 in some way, so let's write that it's minus 2. Yes, so it's minus 1 over 5 times 2 over 5. I mean, of course, with modulus 5 you can just see all the squares. All the squares are 1 and minus 1, because 1 squared is 1, 2 squared is minus 1, 3 squared and 4 squared are the same as 2 squared and 1 squared. So there is no problem here, but of course you can use the general algorithm as well. So minus 1 over 5 is minus 1 to the power 2 times minus 1 to the power 5 plus 1 over 4 integer part. So it is minus 1. So minus 2 is, well, so this number is not a square modulo 73. The conclusion is our congruence has no solutions. It has no solutions modulo the product 59 and 73 because modulo one of them it doesn't have solutions. So x squared has no solution. If one of them is negative 1, then there is no solution. But if both of them are equal to 1, then yes, there is a solution.
How about both of them are negative 1?
If both of them are negative 1, then first of all, there is no solution. And second thing, you shouldn't have computed the second one. Because if the first one is minus 1, that's it. We don't continue. Other questions? Okay, another thing. If you want, well, just for now we're solving just the simplest quadratic equation, x squared is equal to a. If you want to solve a more complicated one, there's no problem. So another exercise. Solve is x squared plus 4x plus 6 is congruent to 0 modulo 101 solve. And the thing is, to solve a quadratic equation, you can always use, well, not always, but usually you can use quadratic formula. And quadratic formula involves, well, out of kind of strange operation, it involves extracting square root and division by 2. If your prime number is not equal to 2, you can't divide by 2, there is no problem with this part of the formula, but extracting the root, well, sometimes you can extract the square root, sometimes you cannot extract the square root. So in this case, well, we'll just see what happens. Yes, so solution. Let's complete the square. That's the simplest way to solve quadratic equation properly. X plus 2 squared plus 2 is congruent to 0 modulo 101. So this equation has a solution. Let me rewrite it as x plus 2 squared is equal to minus 2 modulo 101. It has a solution if and only if minus 2 is a square of something. If it is a square of something, subtract 2 and you will get x. So it has a solution. If and only if negative 2 is a square, is a quadratic equation. And once again, quadratic reciprocity allows you to actually solve this. What is negative 2 over 101? Well, minus 1 over 101 times 2 over 101, which is minus 1 to the power 50 times minus 1 to the power 102 divided by 4 integer part. 1 times minus 1 to the power 25. So it's minus 1. Minus 2 is not a square, so you cannot extract square root of minus 2 modulo 101. So this equation is not solvable modulo 101. Modulo other primes, it could be solvable. Modulo 101, it's not to be solvable. So once again, the conclusion is x squared plus 4x plus 6 is equal to 0, modulo 101. There's no solutions. So, more generally, the usual quadratic formula does work. Modulo a prime number b, which is not equal to 2 modulo any other prime number. So, more generally, x squared plus ax plus b is equal to 0 modulo b means prime is solvable if and only if the discriminant of this equation, the thing of which you should take the square root, is a square. Even only if a squared minus 4b is a square modulo b. And the reason is, well, we can just write the usual formula. Minus a plus minus square root of a squared minus 4b divided by 2. Well, we should inherit everything modulo b. So, if you can extract the square root, we can just find the solutions. And if you cannot extract the square root, the thing with computing the square shows that you can't solve the equation. It has no solutions. Okay. Maybe any questions about this? So another thing for which quadratic reciprocity is useful. Suppose you want to understand something about, well, we've seen an example of this last time. Suppose you want to understand which prime numbers could be divisors of some number of such a form. So fix A, and the question is what primes B could be are divisors of some number of the form n squared plus a m squared. So, for example, if a is equal to 1, the question is what prime numbers could be divisors of the sum of two squares, two relatively prime squares. It turns out that quadratic reciprocity gives you a complete answer to this question. You can figure out exactly what prime numbers could be divisors of such a thing. So let me. more. Let's first figure out the answer here, and then we'll see examples. So solution. Suppose that P is a divisor. So if P is a divisor. So what is the solution?
Let's say that x squared plus 8 squared modulo 0, but common 0 modulo p. So which means we can change it to negative am squared
Okay. Negative 2m squared.
modulo n squared. The common n squared
N squared
modulo p.
modulo p.
And because they are relative prime, so this means we can move n squared to the right side.
Okay, yes. So the next, so first of all, what we did is rewrite this congruence n squared plus an squared is congruent to 0 modulo p in this form. Minus 8m squared is congruent to n squared. Next, I want to divide by this m squared. Can I divide by m squared? Well, I can divide by any non-zero number modulo prime. But is m non-zero? Well, yes, it actually is. So m is not congruent to 0 modulo p, since otherwise, so what happens otherwise? If m is equal to 0, then n is equal to 0. But then both of them is divisible by p. M is congruent to 0 modulo p. M is congruent to 0 modulo p. And then p is a divisor of their greatest common divisor. So it is 1. So we can divide by m squared and get that a minus a is congruent to n over m squared modulo p. In this notation, I'm referring to the number n times multiplicative inverse of n. So this stands for n times inverse of m in the sense of inverse modulo the prime number p. So it doesn't really stand for the fraction, it stands for the residue modulo p, such that once you multiply it by m, you get m. Okay, but this means that minus a is a square. So in particular, minus a over p is 1. So minus a is a square. So from if the prime number is the divisor of such a thing, then minus a is square modulo p. Is the corner square. Is it true that if minus a is a square modulo p, then p is the divisor of some number of such form? Well, let's see. Conversely, if minus a is square, if minus a over p is equal to 1, then minus a is congruent to x squared modulo p for some x. But then x squared plus a is congruent to 0 modulo p. But this number is of such form. It is like this, x squared plus a times 1 squared. So p is the divisor of such number. And of course, x is relatively prime to 1. Every number is relatively prime to 1. So we got a complete answer. So once again, answer b divides n squared plus a m squared for some n which are relatively prime. If and only minus a is a square modulo b. A complete characterization. So during the course we already have seen, well, for the sake of proving that there are infinitely many primes of form 4k plus 1 or 6k plus 1, we've already seen some particular cases of this statement. So example, E is a divisor of n squared plus m squared. Prime, if and only if minus 1 is a square modulo b, if and only if e is. So now I'm using quadratic reciprocity to make this condition make it simple. If and only if e is 1 modulo 4. So if you want to produce prime numbers which are congruent to 1 modulo 4, one of the strategies is, well, produce lots of numbers of this form and look for prime divisors of those numbers. And maybe by some tricks you can arrange all the divisors of the number of this form to be pretty large. For example, take n factorial squared plus 1, something like this. Another example, oh, maybe that's enough for an example. Let's solve an exercise about this. When E is a divisor of such a thing. A little bit harder. Note of the form n squared plus something times m squared. Slightly more complicated. X squared plus xy plus y squared. What can we do here? Let's say yes.
So if I multiply by 2 is x squared plus y squared plus x plus y squared. This is a sum of squares.
Okay, it's a good idea, but well, won't be the directly solution. But it has a very good idea inside of it. Let's try to write this as a sum of squares, it's mainly some coefficients. So we can rewrite this thing. So something like this. X squared plus xy plus y squared. I can complete a square. I can write it with x plus y over 2 squared plus, well, here I have x squared plus 2 times x times y over 2 plus y squared over 4. So I still need 3/4 of y squared. So use this identity. And now let's see. So if E is odd, then, well, then first of all I can divide by 2 and write this identity modulo p. And then I have 0 is congruent to x squared plus xy plus y squared, which is congruent to x plus y over p squared plus 3/4 of y squared. Modulo p. Well, now I can use the previous thing to say that minus 3/4 is a square modulo p, but it's a little bit not convenient. Minus 3/4, what is it? 3 divided by 4, what is 1 over 4? So maybe I will do it like this. This holds if and only if, well, I can multiply my equation by 4 without any consequences. 4 is invertible modulo and code prime p. So I can say that this holds if and only if 2x plus y squared plus 3 times 2y squared is congruent to 0 modulo p. And now I see that minus 3 is a square. So hence minus 3 is congruent to x plus y over dy squared modulo p.
Why did it become 2y?
Good. Oh, it already had all that. Yes, so it's just plus y. Thank you. And here, also there's no g. Okay, and then minus 3. Minus 3 over is equal to 1. And then we can once again figure out what is this condition telling you about p. So this means minus 1 over 3 times 3 over p is congruent to 1. So it's equal to 1. It's just a number. Minus 1 over 3 is minus 1 over p minus 1 over 2. This thing is what? It's minus 1 by quadratic reciprocity to the power p minus 1 over 2 times 3 minus 1 over 2 times p over 3. And you want this to be equal to 1. Well, here you have minus 1 to p minus 1 over 2. Over p. Yes. Thank you. So here I have this whole thing multiplies to minus 1 to the power p minus 1. So it is just 1. So this is the same as saying that p over 3 is equal to 1. And this holds if and only if. Oh, what are the squares modulo 3? There aren't that. Well, basically p is equal to 1 modulo 3. Well, we should have been a little bit careful because when I'm using quadratic reciprocity here, or even when I'm writing the symbol, I am already assuming that p is not equal to 3. So somewhere here, we should say that, well, maybe here, if p is not equal to 3. So one additional constraint. But with 2 and 3, we can actually figure it out. We can figure out what happens. Is 3 ever a divisor of such a number? Is 2 ever a divisor of such a number? So maybe we'll leave it for home. So the homework. It's not a complete solution of the exercise. We didn't do the opposite implications. So homework is p is congruent to 1 over 3. Write same idea as we did with in the previous kind of problem with n squared plus 8 and n squared, exactly the same kind of idea.
So that's inside you want to prove compensated.
Yes, so conversely, so for now we just proved that if P divides such a thing, then P is 1 modulo 3. Now the question is conversely, if P is 1 modulo 3, can you reverse its arguments and say that it is a divisor of such a thing? And yes, we can do this. Okay, so maybe I'll just make an announcement and stop here for the day. So the announcement is like this. The quiz number 3 will cover quadratic reciprocity and exercises on quadratic reciprocity. Next week we'll start doing something which will use a little bit of quadratic reciprocity, but not much of it, and it will use a lot of complex numbers. So yes, a lot of complex numbers. So maybe I want to ask now, how many of you have never seen complex numbers? Okay, 1. So I'll definitely introduce complex numbers next time. We'll introduce multiplication, division of complex numbers. Okay, so we'll start talking about complex numbers next time.
Basically, the stuff so basically all the stuff that's on the quiz is basically just up until today then?
Yeah.
Sounds good.